Hello, everyone. Today I'm going to be going over how to solve problem 46 in chapter 4 in the Fundamentals of Mass and Heat and Transfer textbook, 8th edition. So this problem, which deals with tr transient heat flow, asks us to consider the square channel as shown in the sketch below, which has 9 points and is cut so that we're only dealing with 1/8 of the square instead of the full square. And it gives us 5 of the temperature nodes. It asks us to figure out what are the temperatures at node 2, 4, and 7, as well as the calculated as well as to calculate the rate of heat loss per unit length from the channel. So now over here I've already solved the problem and I'll go through my steps. First, I recreated the sketch, wrote down the values for myself. I wrote down the assumptions, that being that we are dealing with steady state 2D conduction, no heat generation and constant properties. I'm now realizing that I said transient before. That is incorrect. This is steady state that we're dealing with here. So for node 2, we look at it, it's at the very top, which means that it is getting heat through conduction from nodes 1, 3, and 6, and convection from above. So if we put that into an abbreviated heat transfer equation, because there's no heat going out, no heat gen, so it is all heat storage. But since this is steady state, it all evens out, so we can add all these together and equal them to 0. Q1 is via conduction, so that's normally Ka over L delta T. However, in this instance, because delta X is equal to delta Y, what we actually get is it's just going to be equal to K times the width, delta T, and delta T, I am pointing at node 3, but one thing that's also to note is we are only having half of a delta X via the control volume, so that's actually going to be K delta X over 2 delta Y, usually in this instance. I wrote W's for all these ones, but they all cancel out because every term has them. From node 2, we got full conduction, so it'd just be K delta X over delta Y times delta T. Delta X and delta Y cancel out. Then from node 3, it'll be K delta X delta Y, K delta X over delta Y times 2, because once again, it's only half. And then you got the convection, which is just going to be H delta X W times delta T. Once again, W's all cancel out, so it's just going to be H delta X. You can simplify this equation into what I have shown below, and if you solve all that out, you get a temperature of node 2 of 422 Kelvin. Going on to node 4, because it is actually on the diagonal line, there isn't really any heat transferring from along the line, so we can just look at it from node 3 and convection. And in this case, both the conduction from node 3 and the convection from above have their areas halved, so they're both going to be over 2. I have the equation simplified down below, and that becomes T4 gives us 363 Kelvin. Now, going into 7, this one is completely surrounded by nodes on all sides. However, one thing of note is the fact that it is across one of the adiabads, meaning that there is symmetrical temperatures across it, which means that we can analyze it as an interior node with 2 T3s and 2 T6s. So if we put all that, so that's going to be 4 conduction equations using the full delta X, delta Y surface areas. So that equation is going to be 2K delta X over delta Y times T3 minus T7 plus 2K delta X over delta Y times T6 minus T7. You simplify all that together, and you're going to get T7 is equal to 443 Kelvin. Now, for the final part of the problem, it asks us to calculate the rate of heat loss per unit length from the channel. Now, in order to do that, we're going to need to know the conduction, the rate of heat loss per unit length due to convection, which we can do by calculating the heat flows due to convection at nodes 1, 2, 3, and 4. And pretty much how that's going to work out is the equations are going to be H times delta X times W, giving us this H times delta X times the delta T. And in the cases of nodes 1 and 4, it's going to be half because they are on the lines of where we have cut it off. The convection is only going to be half of what it would normally be at nodes 2 and 3 is my equation, and I calculated that the total convection is equal to 156 watts per meter. So that is how I decided to go about solving this problem. I hope that this video was very helpful.